Exponential functions. One of the most important groups of functions in mathematics are the exponential functions. We define an exponential function with base a to be the function f of x equals a to the power x. The number a must be a positive number and it cannot be equal to 1. And this function is defined for all real numbers x. So as a quick example, let's suppose we have the function f of x equals 3 to the power x. The base of this exponential function is 3, which is a positive number, and of course 3 is not equal to 1. So how would we do something like f of 5? Well, f of 5 is just going to be 3 to the 5th power. And of course, this is just 3 times 3 times 3 times 3 times 3. So if we multiply all these together, 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So depending on what you're given, there are some things that you can do without a calculator. For the next one, we have f of negative 2/3. Now this is going to be 3 to the negative 2/3 power. And although there is a definition for dealing with fraction exponents, we're not going to be able to do this by hand since it involves taking a cube root of 3, which we likely don't know without a calculator. So for this, we're just going to go ahead and plug it into a calculator. And you see here, we get this decimal result, and we can choose to round this to however many decimal places we wish. Here, I'll round it to 3 decimal places. So we have 0.481. Now the next one, f of pi, is even a little bit more difficult to imagine because pi is an irrational number. So once again, we'll just simply plug this into a calculator. And we can see that we get 31.5444. And this should make sense. We do know that pi is a number between 3 and 4. And we do know that 3 to the 3rd power is 27. And 3 to the 4th power is 81. So it should make sense that 3 to the pi power should be some number in between 27 and 81. And finally, we have f of radical 2. So this works the same way. We're going to have 3 raised to the radical 2 power. And on a calculator, we have 4.729. So with a calculator, finding values of exponential functions is quite simple, but I think the key takeaway here is that you will need a calculator for many of these values. Exponential functions can be graphed by simply plotting points. So here we have 2 exponential functions. One of them is the same exponential function f of x equals 3 to the power x. And the other one is g of x equals 1/3 to the power x. So here we have the y values for 3 to the x using the following x values. And so you can see what we have there. And then 1/3 to the power x has these y values. And I want you to notice that these y values are kind of swapped here. And that is not a coincidence, okay? That is quite literally due to the fact that 1/3 and 3 are reciprocals of each other. So for example, we know that 3 to the 3rd power is 27. So 1/3 to the negative 3 power, well, the negative flips the fraction over, and then you see we get 27 for that. So there's a reason that these values are kind of swapped like this. Anyway, if you graph these values, you'll find out that the function y equals 3 to the x is this rapidly increasing function. And 1/3 to the power x is kind of the mirror image of this function across the y-axis. And it is a sort of rapidly decreasing function, but then you'll see that it levels off here at the bottom. Now, one thing to notice about both of these functions is that the domain for both of these functions, and in fact the domain for all exponential functions, is all real numbers. And the range of both of these exponential functions and all exponential functions is positive numbers. And this is because if you take any positive number, no matter if it's larger than 1 or less than 1, when you raise it to a positive power, you only get positive numbers. Now let's just talk more generally about how the base affects the graph of an exponential function. So here you can see we have multiple exponential functions graphed. This function right here is y equals 2 to the power x. Then we have y equals 3 to the power x. Then 5 to the power x. And 10 to the power x. And what I want you to notice about all of these exponential functions over here is that they're all pretty much behaving in the same way. They're all increasing exponential functions. They all pass through this point, which is the point 0, 1, and they increase faster and faster as you move along the function. Now, obviously, the base of the exponential function will affect the rate of change. So the larger the base, the faster it's going to increase. On the flip side over here, we have the reciprocals of all of these bases. So we have 1/2 to the x, 1/3 to the x, 1/5 to the x, and 1/10 to the x. And just like we discussed on the previous page here, these are all mirror images of these exponential functions. And you can see that they behave pretty much the same way, but they're just flipped across the y-axis here. So more generally, we can say that the exponential function f of x equals a to the power x, where a is some positive number but not equal to 1, has a domain of all real numbers and a range of only positive numbers, and the line y equals 0, which is just the x-axis, is a horizontal asymptote. And of course, what that means is if you look at the x-axis here, you can see that the exponential function gets close to the x-axis but never touches. And over here, same thing for the x-axis. You can see that it gets close to it but never touches. The graph of f is going to have one of the two following shapes. So as we just previously mentioned, if the base is a number bigger than 1, you're going to have an increasing exponential function. And if the base is a number in between 0 and 1, you will have a decreasing exponential function. So for the next example, we have two exponential functions here. They are both of the form f of x equals a to the power x. The graph is given, and we basically want to find the value of a, right? It says find the exponential function, which means we need to find the base. So if we know that f of x is equal to a to the power x, and in this example, we know that the point 225 is on the graph. Keep in mind that that's x equals 2 and y equals 25. So if we plug those into the function here, we're going to have 25 is equal to a squared. And to solve for a here, you should be able to understand that a is going to either be positive or negative 5 algebraically. But since a is the base of an exponential function, it is only allowed to be a positive number. So a must be 5, and this exponential function must be f of x equals 5 to the power x. For part b, it's the same thing. We have f of x is equal to a to the power x, and in this case, we know that the point 3/1/8 is on the graph. So that means when x equals 3, y is going to equal 1/8. And if we plug those in, we get 1/8 is equal to a cubed. Now to solve this, basically what you would do is you would just take the cube root of both sides. By the way, that's the same step that we would have taken over here, except that we would have taken a square root. And when you take the cube root of a cubed, that's just going to give you a, and the cube root of 1/8 is 1/2. So we know that a must be 1/2, and so our exponential function over here must be f of x is equal to 1/2 quantity to the power x. Now let's briefly talk about transformations of exponential functions. This works exactly the same as transformations of any other kind of function. So we'll start with a simple graph, f of x equals 2 to the power x, which is this exponential function right here, the function g of x equals 1 plus 2 to the power x is just going to be a vertical shift of this function up 1 unit. So that means if your asymptote was down here on the x-axis, your asymptote has now been shifted up 1 unit, and every point on this graph has also been shifted up 1 unit. And so this would be the graph of 1 plus 2 to the power x. For h of x equals negative 2 to the x, remember putting a negative in front of a function is just going to take the graph and flip it over the x-axis. And finally, k of x equals 2 to the power x minus 1. The minus 1 here is going to shift the graph 1 unit to the right. So if the original graph here is 2 to the power x, 2 to the power x minus 1 is just going to shift every point on this graph 1 unit to the right. So every point gets shifted 1 unit to the right. And that's going to make the graph look like this. Now for the second part, it does say state the domain, the range, and the asymptote. So the domain for all of these is all real numbers. So nothing changes for the domain. For the first one here, the range is going to be all y values greater than 1, right? Because now the graph has been shifted up 1 unit, so it's going to approach but not touch y equals 1. So the range would be from 1 to infinity, and the asymptote for that graph is going to be y equals 1. For the second graph, the domain again is all real numbers. The range here is going to be all negative numbers. You can see it in the graph here. We are only getting negative values for y. And so that would be all values from minus infinity to 0. And the asymptote for this one is the same. It's still y equals 0, right? Because the asymptote is still right here. And for the final one, the range is going to be all positive numbers. We can see that the red graph here is still covering all positive values of y. So that'll just be from 0 to infinity. And the asymptote is going to be y equals 0. That does not change. Okay, and so that's for the last one there. In the next example, we compare exponential and power functions. Specifically, we're going to take the exponential function 2 to the x, and we're going to compare it to the quadratic function x squared. So what we want to do is graph both of these functions on different viewing rectangles. So in the first graph, we want to graph for x values between 0 and 3, and for y values between 0 and 8. And you'll see you have your quadratic function y equals x squared here, and you have your exponential function y equals 2 to the x here. Now, you can see these functions behave kind of similarly, right? They're both increasing functions, for example. And this window does give the appearance that the quadratic function is growing faster than the exponential function. And indeed, on this window, it is. However, if you zoom out a little bit and take now x values between 0 and 6, you can see that the quadratic function, which is this blue graph here, is overtaken by the exponential function here at this point. And now the red graph is growing faster than the blue graph. And if you zoom out a little bit more on the window from x equals 0 to x equals 20, you will see that the function x squared is right here, and 2 to the power x is growing much faster than x squared. So of course, your viewing rectangle on a graphing calculator can sometimes make you believe things that are not true. But the takeaway here is that exponential functions grow much faster than any power function. So even if we were comparing it to x cubed or x to the 4th or even like x to the 10th power, the exponential function is going to eventually grow faster than any power function. So one thing that's nice to know is that when an exponential function has a base that's greater than 1, it is a very rapidly increasing function. One of the main applications of exponential functions is compound interest. Compound interest is when a certain amount of money is put into a bank, and we'll call that amount of money P, which is the principal. And we're going to put it in the bank at a particular interest rate per year, which is R. R stands for the interest rate. Now, you have to write R as a decimal, even though it's typically given as a percentage. N will be the number of times the interest is compounded each year. So typical values for N would be 1, 4, 12, and 365. So if N equals 1, that means your interest is compounded annually. If N equals 4, it's compounded 4 times per year, which is often called quarterly. If N equals 12, of course, that corresponds to the interest being compounded monthly, and 365 times per year would mean that the interest is being compounded daily. So these are the most common values for N, but technically N could be any number. And finally, T is the number of years you're going to leave that money in this account. And then the formula says A of T, which is the amount of money you will have after T years, is equal to this formula. Now, I won't derive this formula here, but basically what happens is you get a snowball type of effect. So when you're compounding interest, let's say monthly, after the first month, you're going to add some interest to your money. But then after the second month, you're going to add interest to your money plus interest on the interest. And at every month that goes by after that, you're going to add even more interest on top of the interest that you earned before. And so that's why we say it's a compounding of interest. So as a brief comparison example, let's just suppose that $1,000 is invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. So P is the principal, that's $1,000. The interest rate R is 12%, which is 0.12. The amount of time it's being left in the bank is 3 years, and so T equals 3. And then the compounding number N, for annual, it's 1 time per year. Semi-annual means twice per year. This is not common, but in this case, they want it. Quarterly means 4 times per year. Monthly is 12 times per year, and daily is 365 times per year. So all we're going to do is take all of these values and plug them into this formula. Now, when we do that, we get the following results. And you can see those here. Now, what I want you to notice is not the specifics of all these numbers, but I want you to notice that all of these numbers are generally pretty close to each other. They're all around $1,400. Now, I do also want you to notice that you get the most amount of money when you compound the most number of times per year. In this case, that's daily, right? $1,433.24. And you get the least amount of money when you only compound 1 time per year, and that's $1,404.93. So the number of compoundings is important, right? When you have money sitting in the bank, you want that money to be compounded as often as possible because it does make a difference in terms of how much money you get. However, the most important factor when compounding interest is the interest rate itself. So if you were to slightly increase this interest rate to 12.5% or 13%, you would see much bigger gains in the amount of money that you would get compared to the number of times that you compound the money. So interest rate is the most important factor when calculating compound interest. And one final concept here is annual percentage yield. So the concept here is if an investment earns compound interest, the annual percentage yield, which is often abbreviated APY, is the simple interest rate that yields the same amount at the end of 1 year. So here's an example. We want to find the annual percentage yield for an investment And notice that they don't tell you how much money, because it doesn't matter how much money. And this investment is going to earn an interest rate of 6% per year, and it's compounded daily. So we know from the formula that R is going to be 0.06, N is 365, and the amount of money in the account is P times 1 plus R divided by N raised to the power N times T. Now we're going to plug in what we know. We do not know what P is, but we have 1 plus, interest rate is 0.06, N is 365, and N again here is 365. And then what's T? Well, if I'm finding the annual percentage yield, T is going to be 1 year. So we're just going to plug in T equals 1. Now, when you plug all this into a calculator, you get the following. P times the number 1.0618. And of course, I'm rounding here to 4 decimal places. So what does that mean? It means whatever you put into the bank, whatever dollar value P you put into the bank, it's going to get multiplied by a factor of 1.0618. Now, the 1 just gives you your P back. The 0.0618 is how much interest you will earn. So as a percentage, 0.0618 is equal to 6.18%. And this is the annual percentage yield. So if you are putting money into a bank account at 6% per year and it's compounded daily, basically you're earning 6.18% per year at the end of each year. And that concludes this video lesson.